Dear friends, we talked about very interesting concepts in thermodynamics, including the concept of thermodynamic property and thermodynamic state, thermodynamic process and thermodynamic cycle. An important concept we need to be clear about when we talk about thermodynamic state is we are essentially talking about thermodynamic equilibrium state. So what is that thermodynamic equilibrium state, and how it is important concept in thermodynamics that we are going to study in the next few minutes. We would also discuss in the next few minutes a very interesting concept in thermodynamics which is called as quasi-static process or quasi-equilibrium process. So the objective is to discuss such interesting concepts like thermodynamic equilibrium and quasi-static process. What is this thermodynamic equilibrium? We need to be clear that any system, when you talk about any system, and when we were stating the state of that system having a certain thermodynamic property like pressure P1, volume V1, and temperature T1 at a given point of time, we were assuming that those properties like pressure, volume, and temperature would not change at that moment when we were specifying those properties. And why is that so? That is because that system was in thermodynamic equilibrium. Meaning what? The system is said to be in thermodynamic equilibrium when there is no spontaneous change. Spontaneous, by the word spontaneous we mean on its own. So the system is not going to change on its own. There won't be any change in any thermodynamic property on its own when the system is isolated from its surroundings. And that is because the system would not have any unbalanced forces within the system, as well as there is no unbalanced forces between the system and the surrounding. For example, there is something called as thermal equilibrium, there is something called as mechanical equilibrium, and there is something called as chemical equilibrium. We would be discussing this in detail, but understand that when you say that a system is in thermal equilibrium, what we mean to say is that within that system the temperature is uniform. And also if the system is not isolated and if there is a diathermic wall surrounding that system, then also there won't be any change of temperature, and that would be only possible if the outside temperature is also the same as the inside temperature. Okay, so there is uniformity of the temperature within that system as well as between the system and the surrounding. If it's an isolated system, then obviously the isolated system would not have any energy interaction, and hence even if the outside temperature is different but the inside temperature is uniform, then we would say that that system is in thermal equilibrium. Chemical equilibrium, when we talk about no unbalanced forces, there's no pressure difference, and that is responsible for no change of state, no spontaneous change of state. So when there is no unbalanced force, there is no unbalanced forces between the system and the surrounding, obviously there won't be any spontaneous change, and then that would be a mechanical equilibrium. Absence of chemical reaction would prevent any changes within the system, right? And hence, a chemical equilibrium is defined as a state wherein there is no chemical reaction happening within the system. Okay, so this we would see in more detail. Why is that this thermodynamic equilibrium to be studied? In classical thermodynamics, we know that we are bothered not about the microscopic changes, but the macroscopic changes of the system. So in classical thermodynamics, we consider system being taken from one equilibrium state to another equilibrium state during a thermodynamic process. And hence it is important for us to define what is a equilibrium state, what is a thermodynamic equilibrium. So a system is said to be in thermodynamic equilibrium when there is no spontaneous change in any thermodynamic property, right? So it is a state of balance. In a way, it is a state of balance of a system within itself. And this state of balance, when you have, then we can define certain specific properties at a given time. If it is not in a state of equilibrium, then we cannot define the properties. So that is the relevance of defining the concept of thermodynamic equilibrium. So this pictorially shows you what is a mechanical equilibrium and what is a thermal equilibrium. For example, if you see this system, this system is a closed system. You see there is some gas which is enclosed in the system, and this gas would exert certain outside pressure upwards, right? And there is a ambient pressure which is acting on this piston. Okay, so if this pressure difference is negligibly small, okay, that is the pressure within and the pressure which is outside, which it is infinitesimally small, then there would be no expansion of this gas or no compression of this gas. So in a way, that system would have a force balance. Okay, the balance, and this balance would result in a mechanical equilibrium. Okay, you can imagine a case where there is no mechanical equilibrium. It means that, for example, if the pressure is higher over here than the surrounding pressure, then what would happen? The piston would move upwards, and when the piston moves upwards, it means that there is a process happening. There is no equilibrium, right? So if there is a pressure differential, then there would be inequilibrium. But if there is a balance, perfect balance of the pressure, then we would say that the system is in mechanical equilibrium, right? Similarly, take the second case wherein there are two gases which are enclosed in an insulated container, and these two gases are at two different temperatures, right? So as long as these two gases are at two different temperatures, there would be process happening. There would be a process happening. We cannot say that this system is in thermodynamic equilibrium, right? And if you allow sufficient time, then what would happen ultimately is that both these gases would come at a uniform temperature T3. And when they come at a uniform temperature T3, then and then we can describe this complete system, right, with having a certain specific temperature T3. And we would be doing that because now we would have a system at thermal equilibrium. That is, the temperature is now uniform. Okay, so that is the relevance of defining this concept of equilibrium, right? If there is equilibrium, there is no process happening spontaneously. And if the process has to happen now, if the system has to move from one thermodynamic equilibrium to the other thermodynamic equilibrium, then there has to be certain interaction with the surrounding, either in the form of work transfer or heat transfer or mass transfer, right? So that is to be clearly understood. This concept of equilibrium, thermodynamic equilibrium, leads us to another interesting concept called as quasi-static process or a quasi-equilibrium process. Now, what is this? To understand this clearly, we need to take the help of this figure. Again, we have taken a case of a closed container having a piston. And this closed container having a piston is initially at a thermodynamic equilibrium. It means that the pressure of this gas is, let us say, a pressure P1, volume V1, and temperature T1, right? Now, if you suddenly remove this weight, what would happen? This gas would push this piston, and finally this piston would rest against this stoppers, right? So there would be a sudden change. There would be sudden change from one state to the other state, state 1 to state 2. And when this sudden change happens, this process has happened, right? But that process which has happened is not a quasi-static process because it has suddenly happened, and the states within 1 and 2, between 1 and 2, they are not the states of thermodynamic equilibrium, because in that case, when you consider anything between 1 and 2, you would always find that the pressure is changing, the volume is changing, the temperature is changing, and that is not equilibrium, right? So that is not in a mechanical equilibrium, it is not in the thermal equilibrium. So between 1 and 2, it won't be the system won't be in thermal equilibrium, it won't be in mechanical equilibrium, and hence the system won't be in thermodynamic equilibrium between 1 and 2. And hence we cannot plot that process, right? We cannot plot that process. We would simply say that there is some real process happening between 1 and 2, as a result of which the system has gone from one equilibrium state to another equilibrium state 2, right? If this has to happen, in a manner that each state between 1 and 2 is almost at a thermodynamic equilibrium. And if this happens, then this process is called as a quasi-static or quasi-equilibrium process. Now, how can this be visualized? So we need to do a thought exercise. So what we need to do is that we can imagine this piston, not the piston, I mean to say the weight on this piston, comprising of some infinite slices. Okay, there are you just break this weight into infinite slices, and what you do is that you imagine that this weight, this slice is removed step by step. So let us say you just remove a very small, infinitesimally small slice. Okay, and when you do that, then what would happen is that the system would now move to a small, it would experience a small change, and that would be say 1 dash, and that 1 dash is approximately at 1, and that 1 dash is in thermodynamic equilibrium. Okay, so just we need to do a thought exercise. So when you do this way, that when you are achieving this thermodynamic equilibrium by removal of the slices, and that can be achieved only if the process is carried out infinitesimally slowly. When you are carrying out that process infinitesimally slowly, it means that it is almost static, and that is the why the word quasi-static. Quasi-static means almost static is used. So the process would be quasi-static, extremely slow, infinitesimally slow when you remove these weights step by step. Okay, so this is a very interesting concept, that if you want to achieve a quasi-static process, quasi-equilibrium process, then that has to happen extremely slowly, such that between 1 and 2, all the states are equilibrium states. Okay, so this is an important concept we need to keep in mind. And why is it important for us? So we have understood what is a thermodynamic equilibrium and quasi-static process. We need to think on this, and this is left as a thought exercise for you, that why is this concept very relevant, okay, in thermodynamics, and whether we will be studying what is a reversible process, whether a quasi-static process is reversible process, whether a reversible process is quasi-static process, and what this concept has to do in real life engineering. Okay, so hopefully you have understood this concept of thermodynamic equilibrium and quasi-static process, and I hope you'd enjoy the next concepts also. Thank you very much.